So good morning, everyone, and welcome to today's lecture. This is lecture number 5 in capacitors, and I hope we are able to complete capacitance in today's class. In this lecture, we will start with dielectrics. Do we know what is dielectrics?
Yes, sir.
What are dielectrics?
It is a
Dielectric, yes.
it is a substance which increases the permittivity.
Dielectrics. We talk about the term dielectrics. Dielectric simply means they are insulators. Dielectrics are insulators, and whenever these dielectrics are placed in an electric field, or whenever these insulators are placed in an electric field, they are known as dielectrics. Why they are known as dielectrics? Because there is a microscopic displacement of charge that takes place. Now, every dielectric has got a capacity or strength which is known as the dielectric strength. If you place this dielectric or you place this insulator in a very strong electric field, then they will lose their insulating properties and they will start behaving like conductors. That maximum value of field is known as dielectric strength. So basically dielectrics are insulators. Normally they do not conduct. But when they are placed in an electric field, there is a local microscopic displacement of charges. And because of this local microscopic displacement of charges, there could be an electric field that exists. There would be an electric field that exists inside these insulators. If I increase the value of the external field, at some point, these dielectrics break. They lose their insulating properties. That maximum value of electric field strength is known as dielectric strength. So dielectric strength is the maximum field that can be applied on an insulator so that it remains an insulator and does not become a conductor. I'll give you a minute to note it down fast. Whenever we talk about these dielectrics can be of two types. One is a polar dielectric, one is a non-polar dielectric. Polar dielectric are dielectrics which molecules like water, alcohol, they have a dipole moment in them. The center of positive charges does not coincide with the center of negative charge, and they have a dipole moment of their own. Water molecule has a dipole moment of its own. Whereas there are some molecules like N2O2, benzene, methane, which are non-polar, the center of positive and negative charges, they coincide, and therefore each molecule has zero dipole moment in its normal state. Do we understand this?
Yes, sir.
Now, when this polar or non-polar body substance is placed in a electric field, when there is no electric field, the net dipole moment of the entire thing is zero, even if it is a polar dielectric, because these dipole moments are in random directions. Do we understand this? All these dipoles are in random directions, as you can see in this diagram. So the net dipole moment in the absence of a electric field is zero. Whether it's a polar dielectric, even then the net dipole moment is zero. Even if it is a non-polar dielectric, the net dipole moment is zero. But when an electric field is applied, whether it's a polar dielectric here or a non-polar dielectric here, there is a net dipole moment which is induced. A net dipole moment is induced, and this phenomena is known as polarization. Do we understand what I have said. So whether it's a polar dielectric or a non-polar dielectric, in polar dielectric, each molecule has a dipole moment. The center of positive and negative charges are coinciding. Do we understand this? Sorry. In case of non-polar dielectric, let me give you the heading like this. Then I will give you this table. It will be easier for you to understand the table once you understand each of them separately. So there are two types of dielectrics that we are talking about. One is known as the polar dielectric. The other one is known as the non-polar dielectric. What is the difference between the polar and the non-polar dielectrics? Between the polar and the non-polar dielectrics, polar dielectrics, the center of the positive and the negative charge do not coincide. So each molecule has a permanent dipole moment, but these dipoles are randomly oriented. So the average dipole moment is 0. Do we understand this? But when this is placed in an external field, all the dipoles will align in the direction of the electric field, and therefore there will be a net dipole moment which is induced. In case of non-polar dielectrics, the center of the positive and the negative charges coincide. So each molecule has zero dipole moment. The net dipole moment is also zero. In the presence of external field, they will acquire a induced dipole moment. Do we understand this?
Yes, sir.
Do it fast. Note it down fast. So basically, this is what we are trying to explain. In the presence of or in the absence of electric field, all the dipole moments are randomly oriented. Do you see this diagram number A?
Yes, sir.
Then I put an external field. Let us say E naught is the external field. When I put an external field E naught, what is going to happen? You can see in step number 3, all these dipoles are aligned in the direction of electric field. The direction of electric field is like this, and all these dipoles are aligned in the direction of electric field. Do you see this? Do you see this?
Yes.
Now, because of this alignment, what happens? The net charge inside the space becomes 0 because all these positive and negative will cancel out each other. But what will happen is, here the net charge becomes 0. But what happens is, this negative charge here and this positive charge on this end will get induced. Do we get this? This is known as sigma
Yes, sir.
negative. Do we get this? Yes or no?
Yes, sir.
This is sigma polarization. This is negative sigma polarization. This is positive sigma polarization. So an induced charge, a charge is induced on the outer surface of the dielectric. This charge which is induced is known as bound charge. So whenever a dielectric is placed inside an electric field, a charge is induced on the outer surface. Do we understand this?
Yes, sir.
Because of this charge, which is induced, there will be an electric field that will be produced, and this electric field will be going from here to here. Yes or no?
Yes, sir.
There will be a dipole moment that would be introduced, that will be induced. The dipole moment will be going from here to here. Yes or no? Negative to positive.
Yes, sir.
This phenomena is known as polarization. Do we understand this?
Yes, sir.
You can write it like this. Have you understood this? The alignment of dipole moment in the direction applied of the applied field is known as polarization, or you can also write it like this. Whenever a dielectric is placed inside an electric field, a dipole moment is induced. A dipole moment is induced This phenomena is known as polarization. Do we understand this?
Yes, sir.
So whenever a dielectric is placed inside an electric field, there will be a dipole moment which is induced in the dielectric. This phenomena is known as polarization. I'll give you 2 minutes to note it down. Do it fast. Now, whenever any dielectric is polarized, we denote that polarization, the phenomena, by a vector which is known as polarization vector. This polarization vector is the dipole moment per unit volume. This is dipole moment per unit volume. The magnitude of this dipole moment or this polarization vector is same as the surface charge density, the charge which is induced, sigma I. It is same as the magnitude of the polarization vector, and the direction of P, the direction of P, the direction of P vector is same as the direction of E naught, the external field. Did you see that? Yes or no?
Yes, sir.
Here, I go back to the previous diagram. This was the induced charge. I had called it sigma P. Let me call it sigma I. Sigma I. As you can see, the direction of the direction of the original field was like this, and the direction of the dipole moment which is induced was also in the same direction. Therefore, the direction of this P vector is same as the direction of the direction of the applied electric field, and the magnitude of this vector is same as surface charge density of induced charges. The unit of P is same as the unit of sigma. The dimension is same as the dimension of sigma. I'll give you 2 minutes to note this down. So this is the case. We have an external field E naught. Do you see this external field E naught?
Yes, sir.
This external field E naught is going in this direction. Because of this external field E naught, you have the polarization. This is sigma I or sigma P. On one side, you will have positive charge, and the other side, you have negative charge. Now, because of this positive and negative charge, you will have EP or EI, which is induced in the opposite direction. Yes or no?
Yes, sir.
Now, external field is E naught. The field which is produced inside the dielectric is EP. They will superimpose, and the net electric field will be capital E. Do you see this net electric field E? This net electric field E, if I write it vectorly, this net electric field E will be the superposition of E naught with EP or EI. Do we understand this? If I write it vectorly, it will be like this. If I write it scalarly, it will be E naught minus EP. Do we understand this?
Yes, sir.
I can also write it vectorly like this. This E vector can be written as E naught vector divided by K. And from there, this value of K comes. This K is known as the dielectric constant. This K is known as the dielectric constant. K is 1 for vacuum. K will be infinity for conductors. For insulators or dielectrics, the value of K lies between 1 to infinity. Do we understand this?
Yes, sir.
Do we understand this?
Yes, sir.
Okay. So the formulae that you have to remember here are this. I will mark them. This one. This is the vector formula. This is the scalar formula because they are in different directions. And this is the third formula. This E vector can be written as E naught vector by K. Can you remember this?
Yes, sir.
Also, the next formula that you have to remember is this induced charge density sigma I in terms of the original charge density, and you can remember it like this: sigma into 1 minus 1 by K. We will be using this formula in questions on capacitors. If you want to write the formula in terms of the charges, induced charges will be the original charges into 1 minus 1 by K. I'll give you 2 minutes to note this down. Now, you have to understand what happens when a capacitor is completely filled up with a dielectric. So, if I say that this is the capacitor, this is the capacitor, the distance between the plates is D and the area of the plates was A. The original capacitance of this capacitor was A epsilon naught by D. Do we understand this? We have seen
Yes.
this. This was the original capacitance, yes or no?
Yes.
When this capacitor is filled with a dielectric completely, the new capacitance C dash becomes K times A epsilon naught by D. So you can see C dash becomes K times C, and that is the effect of inserting a dielectric inside the capacitor plate. The capacitance becomes K times the original capacitance. Do we understand this?
Yes.
Do we understand this?
Yes.
Everyone understands this?
Yes, sir.
Now you can see the same diagram in terms of what is happening inside. This is the original sigma which is given to the capacitor. Do we understand this?
Yes, sir.
This is sigma. This is sigma I, which is the induced charges which are coming. Do we understand this?
Yes, sir.
The original E naught is like this. Do we understand this?
Yes, sir.
This original E naught can be written as sigma by epsilon naught. Do we understand this?
Yes, sir.
Everyone is able to understand this, yes or no?
Yes, sir.
This E induced or EP, E induced will be given by a sig. Okay, this induced electric field will be given by sigma I by epsilon naught, and the new field E will be equal to E naught minus EI. Do we understand how we get the value between, how we get the relation between sigma I and sigma? So from here you
Yes.
will get sigma I as sigma into 1 minus 1 by K, because this E is nothing but E naught divided by K. Do we understand this? How we got those relations which were given in the previous case? You have to remember these relations. I'll give you 2 minutes to note this down. Have you understood this? What I've done here?
Yes, sir.
When a dielectric is going to be inserted inside a capacitor, well, the dielectric can fill the entire space inside the capacitor, which we had just seen, or it can fill the space partially. We'll first see the case what happens when the capacitor completely is filled up with a dielectric. We have seen when we have a dielectric completely filling up the plates, The space between the capacitor, the capacitance becomes K times the original capacitance. Yes or no? We have seen that.
Yes, sir.
Now, whenever this question comes, this question will come in two different cases. Now, this thing can be done with battery connected and with battery removed. Now, you must understand what is the difference between the two cases. What happens when battery is connected and what happens when battery is removed. Now remember, when battery is removed, when battery is removed, when battery is removed, the charge on the capacitor will remain constant. Do we understand this?
Yes, sir.
Because when battery is removed, capacitor is an isolated body. The charge of an isolated body will remain constant. We understand this?
Yes, sir.
So on the left hand side, what you see are the values of different quantities when the battery is removed and dielectric is inserted. On the right hand side, we have the battery connected. Do you see the battery connected on the right hand side?
Yes, sir.
We have the battery connected on the right hand side and then the dielectric slab is introduced. What happens in both the cases? In both the cases, you can see the capacitance becomes K times. Do you see this? First listen to me, then I'll give you time to write. In case number one, when the capacitor is isolated, the charge on the capacitor will remain constant, but the voltage will become 1 by K times, the electric field will become 1 by K times, and the energy, the final energy will become 1 by K times. But when the capacitor is connected to the battery and then the dielectric is inserted, the charge on the capacitor becomes K times. Since the battery is connected, voltage drop remains same, electric field remains same, but the energy becomes K times. This is wrong. The energy would become K times. So just correct it. Energy will become K times the initial energy. Do we understand this? The difference between the two cases, yes or no? I'll give you 2 minutes. Now we can see these different cases that I have made in which dielectric slab is inserted. Um, in first case, the original capacitance, as everyone knows, is epsilon naught A by D. Do we understand this? Yes or no? The new capacitance in this case becomes epsilon naught A upon D minus T plus T by K. That is how the formula comes. D minus T plus T by K. From here we can understand the relation between C dash and C. You can write C dash by C will be equal to how much? It will be equal to D upon D minus T plus T by K. Do we understand what is happening here? First, listen to me. Don't write. There is no point of writing. You will not remember anything. You will not understand anything. Have you understood this? First, listen to me. I'll give you all the cases, then I'll give you time to write. There is no point of writing. You are not going to get any time to read what you are writing. Your exam is in next exam is in April. You're not going to get any time to read what you're writing. Understand it? Whatever you can write. You're not going to get any time to revise it or read it again. Writing is immaterial unless you understand it. You understand this formula here?
Yes, sir.
Take a good look at this and remember this formula. This is the formula for the first case. What is the formula for the second case? The original capacitance is epsilon naught A by D. The new capacitance here in this case, C dash. Can anyone give me the formula for C dash? Now I don't have one dielectric. Here there was only one dielectric whose thickness was T and dielectric constant was K. I have a variety. I have a large number of dielectrics with different dielectric constants and different thicknesses. Looking at the formula for one, can you tell me what is the formula for all these put together?
Epsilon naught by A by D
By
minus D minus
epsilon naught A upon D minus
T1 plus T2 plus T3
D minus summation of Ti
into plus
plus
T1 by
summation of
T1.
Ti by Ki. Do we understand this?
Yes, sir.
You can also write it in this way. Epsilon naught A upon D minus summation of Ti minus summation of Ti by Ki. Do we understand this? Yes or no? Or you can also write it like this. Epsilon naught A upon D minus summation of Ti minus Ti by Ki. Are you able to understand what I've written here? Yes or no?
Yes, sir.
Yes or no?
Yes, sir.
In the third case, the original capacitance is epsilon naught A by D. The new capacitance will be how much? Epsilon naught A upon here the entire space is filled with dielectric and there is no empty space. So it is simply
Summation
becoming
Ti by Ki.
summation of Ti by Ki. Do we understand this?
Yes, sir.
Now I'll give you time to note it down. Once you've understood this, you don't have to look at the diagram. You can draw your own diagram and write the formulae. These are not formulae, these are questions that are going to come in your exam. Okay, this was the case when a dielectric slab is introduced. Now, instead of a dielectric slab, sometimes you will see a metallic slab being introduced. A metallic slab being introduced within the plates of the capacitor, like this, case number 1. A metallic slab is introduced. Now, this is case number 1 and this is case number 2. Case number 2, both of these cases are same. I mean, on the left hand side you have case number 1 and in the right hand side you have case number 2. In case number 2 there are two cases given. In first case, the conducting material is completely filling up the space. In second case, there is just a wire which is connecting the two plates. So on the left hand side, you have a conducting plate or conducting slab or metallic slab which is not filling up the entire space. In case number 2, we are filling up the entire space. If you want to call the third case as case number 3, a wire is connected between the two. In fact, I will call this as case number 1 and this entire thing as case number 2. Can you tell me, by whatever we know already, what will be the capacitance in the first case? What would be the capacitance in the first case?
epsilon naught A by D minus T, sir.
The original capacitance was obviously equal to epsilon naught A by D. The new capacitance, remember, the K for a conductor is infinite. So it becomes epsilon naught A upon D minus T, because T by K is 0. Do we understand this?
Yes, sir.
In case number 2, whether you talk about the first subset or you talk about the second subset, in both the cases, the capacitance becomes infinite. Do we understand this? Or this is not defined for such cases. Do we understand this? So when you connect two plates of the capacitor to each other, nothing happened. This capacitor goes out of the circuit. Do we remember this? Do we understand this? Yes or
Yes, sir.
no? No, yes. Do we understand this?
Yes, sir.
Now, one more thing you must understand, this capacitance in all these cases does not depend on this capacitance in all these cases does not depend on the position of the slab. The position of the slab. If this slab here is put here or it is placed anywhere in between, it does not make any difference. The capacitance still remains same. Do we understand this?
Yes, sir.
Similarly, in all these previous cases, no matter where I place the dielectric slab, if I change the position of this slab and I put it somewhere else, but I should not change the thickness and I should not change the dielectric constant, wherever I put it, the capacitance will remain same. Capacitance does not depend on the position of these slabs. Do we understand this, or this has gone above our heads? Saying bye bye.
Understood, sir.
Anyone understands this? Yes or no? Can I have raised hand from everyone that we understand this? This is one way of doing this question, that we do it by direct formula. There is one more way of doing this question by series parallel combination. How can you do the same? How can you find out the capacitance by series parallel combination? It is easier to understand it in terms of the third diagram. We can take this capacitor as C1, you can take this capacitor as C2, you can take this capacitor as C3, and all these C1, C2, C3, how are they connected?
Series.
They are connected in series. So instead of you using the formula straight away, you can find out the capacitance of each of them individually, and then you can take them in series. That is the next way or the other way of doing the same thing. Do we understand this?
Understood, sir.
Or this has gone above our heads? Saying bye bye. Bye bye.
Understood, sir.
Pakka, sir?
Yes, sir.
Okay. Now this is one type of distribution where they are completely filling up the area and the distance is divided. This type of filling, partly filling, is known as distance division, because they are dividing the distance. Do we understand this? Partly
Yes, sir.
filling distance wise. Do we understand this?
Yes,
Partly
sir.
filling distance wise. Therefore, you can have one more scenario in which they are partly filling but area wise. And I will just give you a very simple example. Partly filling area wise, you can take the example of this one. You can take the example of this one. This is partly filling area wise. Dielectric constant of this one is K1 and area is A1. Dielectric constant of this is K2 and area is A2. Do we understand this? Yes or no?
Yes, sir.
Now you can take the capacitance of this as C1 and you can take the capacitance of this as C2. Do you understand this?
Yes, sir.
C1 will be in parallel with C2. Do we understand this?
Yes, sir.
The value of this C1 will be equal to K1 epsilon naught A1 by D1. Do we understand this?
Yes, sir.
This D1 and D are same because they are filling up the entire space. Do we understand this?
Yes, sir.
The value of this C2. Can you tell me the value of this C2? What will be the value of this C2? K2 epsilon naught A2 by D. So I can there from there you can find out the effective capacitance. Effective capacitance will be C1 plus C2. Epsilon naught by D will come out and you will have K1 A1 plus K2 A2. So this is one case which you can do of partial filling, not distance wise, but partial filling area wise. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. So this is the next question, sir. A dielectric of dielectric constant K is slit between the plates of a parallel plate capacitor, parallel plate condenser in half of the space as shown in the figure. The capacity of the air condenser is C. When I say capacity of the air condenser, that means when it was completely filled with air, the capacitance was C. Do we understand this?
Yes.
What will be the new capacitance? Half of it filled with a dielectric of dielectric constant K. The original capacitance is C. I'll give you 2 minutes to give me the answer. Option C is correct. Either you can do it by a series parallel combination or you can, I've already given you the formula, right? So you can apply that formula only straight away. You can apply that formula. C is equal to epsilon naught by D into, what was the formula? K1 A1?
A1 A1 plus K2 A2.
K1 A1 plus K2 A2. Here K1 is 1, A1 is A by 2. You should do it correctly. K2 will be K, A2 will be A by 2. If you do it correctly, you will land up here. Yes or no? No, yes.
Yes, sir.
Do we understand this?
Yes.
Then this is the next question. And if you can do this, then we can move ahead in life with the other type of questions. You have to find the effective capacitance between A and B. I'll give you 2 minutes to give me the answer. I hope you can do this. Yes or no?
Yes.
Do it. Calculate it correctly and give me the answer. So how are we supposed to do this? Let us quickly do it. Let us not waste any time. Let me call this as C2. Let me call this as C3, C2 and C3. So I can find out the value of C1. What is the value of C1?
K1 epsilon naught A1 by D. D.
A1, K1, epsilon naught by
D1 plus D2.
D1 plus D2. The value of C2 will be K2, A2, epsilon naught by D2 and the value of C3 will be K3, A3, epsilon naught by D3. Do we by D2? Do we understand this?
Yes.
Yes or no?
Yes, sir.
This C2 and C3 are in series, yes or no?
Yes.
And then it is in parallel. Do we understand this?
Yes, sir.
So when you solve it, I am telling you the answer. This is the answer that you are going to get. This is the answer that is given in the sheet. This, as you can see, is the capacitance of C1. Do you see this? And this entire thing will become the series combination of C2 and C3. So you can note down the result, and I hope you understand how it is done. Do we get this? Yes or no?
Yes, sir.
Have you noted it down?
1 minute.
Give you a minute. That takes us to the next setting for this. This is the plate, the attraction, the force between the two plates of the capacitor. As you can see, one of the plates of the capacitor is positively charged and the other plate of the capacitor is negatively charged. They are going to attract each other, yes or no?
Yes, sir.
The force of attraction between the plates of the capacitor is given by this formula. You can remember it in terms of sigma, which is the surface charge density, or you can remember it in terms of Q, which is the charge given to the plates. This plate is having charge plus Q, this plate is having charge minus Q. I'll give you 2 minutes to note this down. And this is the first question that is going to come. The mean electrical energy density of electric field. If you remember, we have discussed this. Between the plates of the capacitor, which of the formula is applicable for the energy density between the plates of the capacitor? I'll give you a minute. Option A is correct. If you remember, the energy density du by dV was half epsilon naught E square. Do we remember this?
Yes, sir.
The only option that matches is half into epsilon naught E is sigma by epsilon naught, and you can get the answer. This is option number A, and I hope you will remember it. Yes or no? No or yes? Everyone understands this?
Yes, sir.
Next question. Plate separation of a 15 microfarad. So original capacitance 15 microfarad is 2 mm. A dielectric slab of thickness 2, thickness 1 mm, and dielectric constant 2 is inserted between the plates. What is the new capacitance? And the answer is, I've already given you the formula. C dash by C will be equal to D upon D minus T plus T by K. You just had to put the values, get the answer, and stay happy. And the answer that is coming, when you put the values here, I think is 20 microfarad. That is the answer. The value of C here was given as 15 microfarad. The value of D here was 2 mm. The value of T here was 1 mm. And the value of K here was 2. I hope you understood how to do. Let me move on to the next question. And this is the next one. I'll give you 1 minute, 2 minutes to solve this. There is an air-filled capacitor, 1 picofarad. When the plate separation is doubled and the space is filled with wax, the capacitance increases to 2 picofarad. What is the dielectric constant of the wax? Option B, all of us know this. The original capacitance is given by epsilon naught A by D. The new capacitance is given by epsilon naught into K into A divided by 2 times D. It is given that the original capacitance has become 2 times. The distance has also become 2 times. Therefore 2D. I think from there you can calculate that the value of K will come out to be 4. We understand this, yes or no?
Yes, sir.
Everyone understands this?
Yes, sir.
Next question, do it fast. The force between the plates of a parallel field capacitor of capacitance C, distance of separation is D, and the voltage potential difference is V is given by which formula? So I've already given you the formula of force, yes or no? From there
Yes,
you
sir.
can calculate. What was the formula of force that I gave you?
Q square by 2 epsilon naught A, sir.
2 epsilon naught A, and this Q can be written as CV. Yes or no?
Yes, sir.
And epsilon naught A by D can be written as C. So epsilon naught A becomes C into D. From there you can just eliminate the terms and you will get this answer. Yes or no?
Yes, sir.
You could have got this answer by dimensional analysis also. There is only two answers whose dimensions are correct, and those two answers are A and D. Half has to come, therefore the only correct answer has to be A. That way also you could have done this. I don't know which process was simpler, doing it by dimension analysis or doing by it by this way. Anyways, I hope you know all the all the ways of solving it. You just need to solve it in the easiest possible way. This is the next question. A capacitor is filled with a dielectric of dielectric constant 3, has charge. Initial value of charge is K naught, Q naught, V naught, E naught. If the dielectric is replaced with another one having dielectric constant 9, what are the new values? So the correct option is option D. The charge has to remain constant. The charge has to remain Q naught. So the only options are B, C, and D. C option is not possible because if voltage has to change, electric field also needs to change in the same ratio. Voltage and electric field are not going to become 3 times. They are going to become divided by 3. Yes or no? So the correct
Yes, sir.
option is option D. I hope you are able to understand what I am saying here. Yes or no?
Yes, sir.
Next question. Give me the answer first. A copper slab of thickness B is inserted between the plates of a parallel plate capacitor as shown in the figure. The separation between the plates is D. If B is equal to D by 2, then the ratio of capacities of the capacitor after and before inserting the slab is how much? Option B, I have already told you, the initial capacitance C is epsilon naught A by D. The new capacitance C dash becomes epsilon naught A upon D minus B. B is D by 2. Yes or no?
Yes, sir.
The correct option has to be option B. Anyone understands this?
Yes, sir.
This is the next question. The capacity of a parallel plate capacitor is C naught. If a dielectric of relative permittivity ER, you can call it as K if you want to, and thickness equal to 1/4, the plate separation is placed between the plates, the capacitance becomes C, ratio of C by C naught. Do it fast. Well, I have already given you original capacitance is epsilon naught A by D. The new capacitance C dash will become epsilon naught A upon D minus the thickness. What is the thickness? D by 4, yes or no?
Yes, sir.
Plus thickness T by K. So D by 4 divided by epsilon R. Yes or no? From
Yes,
there
sir.
you can find out the ratio, and I think the ratio that you are going to get would be this one. Everyone got this? Yes or no?
Yes, sir.
That takes us to this one. A air capacitor of capacity C is 10 picofarad is connected to a constant battery. So battery is connected here, 12 volt. Now the space between the capacitor plates is filled with a liquid of dielectric constant 5. The charge that flows from the battery to the capacitor. When the dielectric is inserted, how much charge has flown through the capacitor? How much charge has flown to the battery? Give you 2 minutes to give me the answer. Do it again. The original capacitance is 10 microfarad and the battery is 12 volt. So the original charge is 120 microcoulomb. Yes or no?
Yes, sir.
The new capacitance becomes 10 multiplied by 5, 50. So the new charge becomes 600 microcoulomb. Yes or no?
Yes, sir.
So from 120 microcoulomb, the charge has to change to 600 microcoulomb. So how much charge will flow? Extra charge that will flow. That extra charge would be 480 microcoulomb because 120 was already there, and now we have to make it from 120. We have to make it to 600. The extra charge that has to flow would be equal to 480 microcoulomb. Do we understand this, everyone?
Understood, sir.
Yes or no? No, yes.
Yes, sir.
Well, that brings us to an end of this particular section. Now we move on to the last section of capacitor, which is charging and discharging of capacitor. I'll give you 2-3 minutes. Go back. If there's any doubt up till here, please ask. I'll give you 2-3 minutes. Go back up till this part. If you have any doubt, please ask, because after this we will be finishing up your capacitors and there is no chance that we are going to come back because it's no time for us to come back. Give you 2-3 minutes. Go back, have a look. So that takes us to the last part of this capacitor chapter, which is charging and discharging of the capacitor. What is this charging and discharging of the capacitor? We can talk about 3 different stages of RC circuit. Now, you must remember that whatever happens, whatever I make in any circuit, even if I do not put any resistor, any circuit, even if I do not put any resistor, it will have wires, it will have a battery. So there would be some resistance of the circuit even if there is no resistor put. Do we understand this? So every circuit has a resistance. Now if I put a capacitor, so this now becomes a DC because it's direct current RC circuit. Now whenever we are talking about this RC circuit, any circuit always has a switch. So whenever we are talking about this RC circuit, we can talk about 3 different stages. The first stage is when the switch is just put on. That is known as the initial state. Put is just when the switch is just put on, just switch on. That is known as the initial state. The second state is known as the transient state. Now, what do you mean by transient? Transit visa, if you understand. Transient state is the stage which is any time after closing or opening the switch. Here we have closed the switch. So it is the state any time in between that. Why it is known as the transient state? It is known as the transient state because the charge on the capacitor will keep on changing. This is the diagram if you want to draw of a transient state. In a transient state, what is going to happen is Q, V are variable. The charge of the capacitor starts to get charged, but at any time the charge on the capacitor is not constant. It keeps on changing. Do we understand this? This is known as the process of charging of the capacitor. Do we understand this?
Yes, sir.
Do we understand this?
Yes, sir.
Then the third state, and this is the state up till now what we were studying, is known as the steady state. In this steady state, what happens, my dear friends? The charge on the capacitor becomes constant. The charge on the capacitor becomes constant. The potential difference across the capacitor plate also becomes constant. This state, my dear friend, is known as the transient state. Do we understand this? All the three stages which are on your screens now. The first one is the one where I have just put on
Excuse me.
the first one is the one where I have just put on the switch.
Hello, sir.
The second one, the capacitor is getting charged.
Hello, sir. Excuse me.
And the third is the stage where the capacitor has fully
Hello, sir.
charged. That is known as the steady state. Yes.
Sir, the power is gone and it is running on the backup.
Okay.
Backup is also completed. So the system is going to shut down. So
Okay.
you
So
should
then
make.
I will wind up the class now.
Yes, sir.
Okay. So you can draw this diagram up till here. You can draw the diagram up till here. And we will start from this point on in the next class. Okay. You can note it down up till here. I'll see you in the next class. Okay. Bye bye.
Yes.